Hello, and welcome to Chapter 7, Alkyl Halides, Substitution and Elimination Reactions. In this chapter, we will discuss the role of halogen in terms of the role it plays in substitution and elimination reactions. We will learn how to assign names and classifications to alkyl halides, describe details of SN2 type reactions, discuss the effects of nucleophilic strength and solvent identity in substitution reactions, describe E2 reactions, the relationship between the structure and stability of alkenes and cycloalkanes, describe the factors that affect the outcome of an E2 reaction, including regiochemistry and stereochemistry. Describe the process that happens when SN2 and E2 mechanisms compete. Explain what happens when an SN1 reaction and an E1 reaction, including the rate equations, mechanisms, energy diagrams, rearrangements, substrate effects, and stereochemical outcomes. Predict the products of reaction. Determine how alcohols and alkyl sulfonates behave in substitution and elimination reactions. Perform central synthesis analysis, and describe the effect of solvents in SN1 and SN2 reactions. Let's start by describing what is an alkyl halide. An alkyl halide is a group that contains hydrocarbons and a halogen. Halogens are typically described using a letter X, and what that means is that it can be chlorine, bromine, or iodine, just any one of them. Alkyl halides undergo substitution and elimination reactions. And here, just as a quick review, we have 4 bonds in this carbon atom, making it an sp3 hybrid, 3 bonds, and a double bond, sp2, and here, sp2 hybrid as well. Alkyl halides can undergo substitution reactions when reacted with a nucleophile, something with a lone pair of electrons, negative charge, something that likes those positive charges. That's where nucleophile name comes from. Alkyl halides can also undergo elimination reaction when reacted with a base. Now, when you look at nucleophiles, like here the generic name for a nucleophile, and you look at a base, what do you see in common? We see this lone pair of electrons and the negative charge as well. As you can see, this will be a substitution reaction. You change that halogen for whatever the nucleophile is, and in the case of an elimination, you remove your halogen, you also remove a hydrogen to form a double bond. When the reagent can act as both nucleophile or base, elimination and substitution will be competing reaction pathways. This is going to be a common theme throughout the chapter where we see substitution, elimination sort of going hand in hand, and depending on conditions, depending on solvents, and a number of other factors, we will see that one of the pathways, substitution or elimination, is favored over the other. In this case, for instance, we have a strong base, we have an alkyl halide, and the substitution happens to be a minor product. As we mentioned on the past slide, strong base will typically undergo elimination. So in this case, you get both products, but your elimination product is your major product. Two main reasons why alkyl halides undergo substitution and elimination reactions. The halogen, as you know, fairly electronegative, so it is electron withdrawing, it's pulling that electron cloud towards itself. It creates a partial positive charge on the adjacent carbon, making it susceptible to a nucleophilic attack. Another way of looking at it is that this bond between carbon and halogen is fairly weak because the halogen is pulling that electron density towards itself. The halogen will act as a leaving group. This is the term that we use for whatever is leaving the system, generating an intermediate, a carbocation intermediate. And for a substrate to undergo a substitution elimination reaction, it must possess a good leaving group. In other words, this setup that we have here has to be met for any of this to happen. Good leaving groups are the conjugated bases of strong acids. This is a very important concept that you should familiarize yourself with early on because it will allow you to perform analysis of synthesis much easier later on. You can see your stronger acids, the conjugated bases of them, that means the deprotonated species, they make for very good leaving groups. And as our acids become weaker, the leaving groups are not so good. Alkyl halides are compounds where a carbon group, or the alkyl, is bonded to a halide or a halogen, as we mentioned before. These are some of the steps, just like we saw before, For naming alkyl halides, we identify the parent chain, we name the substituents, we assign number to the substituents, and then we put everything together alphabetically. The halide group is the key substituent we will name and locate. That's the only big difference between alkyl halides and everything else we've done up to this point. For each of these examples, convince yourself that they are numbered in the most appropriate way. Let's go over each one of these. We have 2-chloropropane, so we're going to look for the longest chain, 1, 2, 3. So it could be from left to right or from right to left. In any case, position number 2 will have the chlorine, so we use the word chloro instead of chlorine, and we indicate where it's located. So in position number 2, chloropropane. That will be the name of this compound. Let's go to this one. Here we have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Doesn't really matter. You're going to end up in the same place. You could also number from right to left. 1, 2, 3, 4, 5. If you go from right to left, as opposed to what we already have here, your bromine as well as the methyl group you will have as a substituent will be in position number 4. If you go from left to right, then position is number 2. And as we mentioned before, lower number is always preferred when naming compounds according to IUPAC. So we're going to go with numbering from left to right. Position number 2, we have a methyl, we have a bromo. Between methyl starts with an M, bromine starts with a B, so B goes first. 2 bromo, 2 methyl, and then pentane. Lastly here, we actually have a chirocarbon, so we have to make sure that we know whether it's an R or an S. We go from left to right. In position number 2, number 3, and number 5, we have substituents. If we go from right to left instead of what we have here, we will have substituents in position number 3, 6, 5, and 6. These are higher numbers, so we go with left to right. We have a methyl group in position 2, 3, and 3, so 2, 3, 3, trimethyl. Position number 5, we have bromo. This is an R chiral center, so R, 5 bromo, 2, 3, 3, trimethyl heptane. Some simple molecules are also recognized by their common names. So for instance here, this is methane, only one carbon atom, so iodomethane. It can also be labeled or named as methyl iodide. This is actually a historical name. This is before IUPAC. And if you go to any stockroom and you find really old reagents, you are going to see some of them named this way instead of this way, for no specific reason, really. The alkyl group is named as the substituent, and the halide is treated as the parent name. 2-chloropropane, that will be isopropyl chloride, and for 1-bromopropane, it will be N-propyl bromide. Greek letters are often used to label the carbons of the alkyl group attached to the halide. Now this is important, and we are going to see it again later on as we keep moving towards reaction mechanisms, things of that nature. The carbon attached to your halogen in this case will be the alpha carbon. If you move one carbon away in any direction, you get beta carbons, and you keep moving, you have gamma, and then delta, epsilon, etc. This is important because later we will see alpha carbon, beta carbon. You'll see. The amount of branching at the alpha carbon affects the reaction mechanism. There are 3 types of alkyl halides. When you only have one carbon atom, no real branching, just a chain, you have what we call a primary alkyl halide. When you have one branching, so 2 substituents are splitting up, you have a secondary, and when you have 3 of them, you have a tertiary alkyl halide. There's no such thing as a quaternary alkyl halide because that would imply that carbon has 5 bonds, which, as we know, is a cardinal rule. Carbon does not have. Some applications, including insecticides, like the ones we see here, DDT, lindane. You will also see alkyl halides in dyes, drugs, food additives, and many more. So alkyl halides are super common in industry, some of them in nature. That's why we are actually taking an entire chapter just to study them, how they react, what we can do with them, etc. Simply because of their importance in chemistry in general, really. Now let's talk a little bit about the SN2 mechanism. SN2 is an abbreviated form. S stands for substitution, N stands for nucleophilic, And 2 stands for bimolecular. That means that 2 molecules are involved in um, that defining step, that reaction rate determining step in the process. So substitution, nucleophilic, bimolecular. A substitution reaction requires the loss of a leaving group. We kind of saw that at the beginning of the chapter. And a nucleophilic attack. So two things are required for a substitution reaction to happen. There are two possible mechanisms. Either both things happen at the same time, we call that a concerted reaction, or they happen one after the other, which would be a stepwise. The concerted mechanism involves breaking of the bond to the leaving group and making of the bond to the nucleophile at the same time. Concerted mechanism, we can see here, for example, the electrons here are sort of going towards your halogen, so this bond is breaking, and the nucleophile is attacking or making itself bound to what would be a carbocation in that area. No, for conservative mechanisms, you can see from here that a feature or something that is very important is for this to be able to happen physically, it can't be impeded. So if I have a lot of branching, some steric groups here, then as this type of concerted mechanism doesn't really take place. In any case, the product will be your nucleophilic substitution and then your halogen. In the stepwise mechanism, the leaving group leaves first to give a carbocation intermediate, followed by a nucleophilic attack. So for this one, you see the arrows are actually split into two steps rather than just one. So the first arrow will be your halogen leaving, and then your nucleophile sort of attacking that carbocation. Now for this, the most important part is for your carbocation to have some stability. So whatever alkyl groups, right? Whether you have a lot of branching, you have a lot of aromatics, etc., something that allows for that carbocation to exist now in a measurable amount of time, that would allow for a stepwise process to actually happen. If it doesn't, if it's not really stable, that carbocation, then it can't go through the stepwise process, it goes through the concerted process.